Good afternoon, everyone. For the very last time, I'm so happy that so many of you decided to join us today and enjoy the pizza and enjoy one last round of algorithms before I send you off into the world ready to change things. So I have said that we're done with all the core content, so this is your chance to tell me what's going on at each stage of the lecture. So we're going to go over to you for everything that I'm doing in here. We'll keep the content a little short and then a fun surprise at the end. So you'll remember, like earlier in semester, maybe if you were on Ed, you looked at this challenge of generating the nth Fibonacci number. And by now, I hope that you're all experts, and any one of you should be able to give me at least one technique for computing the nth Fibonacci number. But I know some of our memories aren't so good, so we'll do a bit of a refresher and a little bit of motivation before we get all the way there.
The human X chromosome contains hundreds of genes associated with a wide range of diseases, including hemophilia and red-green color blindness. An interesting aspect of the X chromosome is its inheritance pattern. Unlike the Y chromosome, where the number of possible ancestors must be equal to the number of generations, or the 22 other autosomes, where the maximum number of possible ancestors is equal to 2 to the power of the number of generations, X chromosome inheritance is a little more complicated. A male will inherit one of 2 possible X chromosomes from his mother, either from his maternal grandmother or his maternal grandfather. A female will also inherit one X chromosome from her father, introducing an asymmetry in the number of possible ancestors. Turns out there's an efficient way to calculate the number of possible X chromosome ancestors using the Fibonacci sequence. For a male, the number of possible ancestors is equal to the nth Fibonacci number, where n is equal to the number of generations going back. For females, this method can also be used, but n is equal to the number of generations plus 1.
So that is a good friend of mine, Michael, who graduated from the University of Melbourne just a few years ago and is now working in one of the very exciting startups around the corner. But I know that not all of you are here for the biology, so we will focus on the computer science part of this. But aside from like these nifty little things in biology that motivate why we might want to calculate the nth Fibonacci number, there's also a reason that might be closer to a number of your hearts, which is that this puzzle is almost always used in programming interviews of one sort or another. So I've probably done 3 or 4 job interviews in my time, particularly when I was a student, where this was the problem that they gave me. And what I want to do in the first half of today's lecture is to give you all the tools to really excel at this so you can like blow the interviewers out of the water and even give them surprises about this problem that they didn't know. So our task is to calculate the nth Fibonacci number. And I don't have a nice handheld today because of our change in circumstance. But for the recording, we're still going to use this microphone once it's switched on. Chen, before you run away, take the microphone and give it to anyone you like.
Anyone I like?
Yeah, or anyone you don't like.
Well, I prefer anyone I like.
So hurry up, they're about to be asked a question, so you get to pick the victim today.
Who's going to be answered? No?
Okay, you got it. Now you have to answer. So tell me, what's the formula that determines the nth Fibonacci number? Or let's start a little simpler. What is the Fibonacci sequence?
So you start with, was it 0 or 1?
Start with 1.
You start with a 1, then the next number is 1, and based on that, the next number would be the sum of the previous 2 numbers.
Yeah, so the Fibonacci sequence works by taking the prior 2 numbers and summing them together to get the next number. So if we were to write this out, and I'll do this just on Visual Studio Code here, we always start with a 1 and a 1, and then the next number is the sum of the 1 and the 1, so
2.
2, and 1 plus 2?
3.
3, and 3 plus 2?
5, then 8.
8.
And 13.
13. Okay, so our general idea is to take the prior 2 numbers and add them together to get the next number over here. Right? And then we just keep repeating that over and over and over. So we could also write that in various series of forms actually in the code to generate that for us, rather than having to do the addition manually each time. So do you want to give me at least a sketch of how we could do this? It doesn't have to be perfect C code, because we're very well practiced at this point.
We could use recursion.
Recursion sounds great. That's what I was hoping for. Okay. And
so we need a base case. So
okay, base case.
if n is equal to 0, then you return.
Well, let's start the sequence at 1, but maybe we'll leave that 0 in anyway. So for the 0th Fibonacci number or the first Fibonacci number.
Yeah. Then you return, is it 0?
Well, let's do, if n equals 0, let's return 0, right? And just say that's an invalid case. Okay. For the first Fibonacci number and the second Fibonacci number, what do we get?
You get 1.
So we actually need another base case here just to account for the fact that 0 was an invalid choice, so that's like an erroneous input. But this is our real base case, where n is 1 or n is 2. OK. And outside of the base case?
So then you have the recursive case, where you continuously call fib n-1 and n-2 afterwards. So it's the sum of, you return the sum of...
Oh, so I return, OK, return fib n...
-1 plus fib n-2.
n-2. So that's pretty good. Let's call this fib instead of rec. That makes more sense. Now, this is exactly what I proposed we do in my slides. Fib of f of 1 is 1, f of 2 is 1, and then f of n is just n-1 plus n-2. So this is pretty easy to code, and if we were to work out the runtime, which we're not going to do today, we would get O of 1.7 to the n. Now, pass it on to Tissan. Is this a runtime that makes us happy or sad?
It's not that good.
Not that good.
Yeah.
So give me a little more. What's the problem with it?
It goes exponential, so it's
Yeah, it's
not very good.
exponential.
Yeah.
It doesn't have a super high, like it's 1.7 to the power of n, which isn't as bad as it could be. It would grow a lot faster if it was, say, 10 to the n, but still with 1.7, we're still in exponential territory. We're probably not pretty happy. But let's take a look at the version I coded earlier to do this properly in C with all the bells and whistles. And this time, I'm actually going to use a long, because the numbers in the Fibonacci sequence are going to grow pretty quickly, and so I want to have room for larger numbers. So remember, we had an integer, which was typically on our systems 32-bit, a long typically 64-bit, and a long is often going to be 128 bits. So that gives us a lot more room to play with for large numbers. So which Fibonacci number do you want to calculate? All the normal intro stuff for our function, and then our recursive case, which looked almost identical to what we did before. So let's compile it. Fib1, and then it's going to say which Fibonacci number do you want to calculate. Let's just try 1. OK, that works fine. What about the fourth Fibonacci number? Fourth Fibonacci number was 5, and it's actually going to give us a trace of what recursive calls it's made. So in order to calculate the fourth Fibonacci number, it had to calculate the third Fibonacci number, the second Fibonacci number, and the first Fibonacci number, and that's just for one of the 2 recursive calls. For the other recursive call, it's going to calculate the third Fibonacci number, the second Fibonacci number, and the first Fibonacci number. Actually, let me say that correctly. It has to calculate f of 3 and f of 2, and the way it calculates f of 3 is by calculating f of 2 plus f of 1, and the way it calculates f of 2 is by doing f of 1. So that's going to lead to a whole lot of recursive calls. We've got 2 sets of these, and there seems to be something that we're doing over and over. Blake, do you want to take the microphone from Tissan? Where am I wasting work here?
Oh, you already calculated most of the previous ones, and you're redoing them for every next number.
Yeah, so remember I've got these 2 recursive calls. I've got fib n-1 and fib n-2. But most of fib n-2 is already captured in the work that I did for fib n-1. Because in order to calculate n-1, I I had to have calculated n minus 2 anyway. So it seems like I'm doing some waste there. So let's see how bad this problem is in practice. So I'm going to run my fib thing again, and I'm going to try the 50th Fibonacci number. And we're just going to leave that running for a minute. Now, Aditi has been thinking very hard about this one. I've seen it on her face for the last couple of minutes, so let's get the microphone to her. Right over here. So you're very upset by this, I can tell, right?
Yeah.
Okay, so what should I have done?
You should have reduced the need to have calculated both fib n of 1 and n of 2.
Yeah, and well, ultimately I am going to need the answer to both of those values, right?
Yeah.
But you said I was wasting work because I've already done it. So if I've already done work and we want to reuse it, what do we typically do?
You would store it?
Yeah, we'd store it. And so how would you store the first Fibonacci number, the second Fibonacci number, the third Fibonacci number, the fourth, the fifth, the sixth? What kind of data structure would you use? Something very simple.
An array?
An array, right? So what we can do is as we go ahead and calculate our Fibonacci numbers, we can store them in an array and then check to see if we've already stored it in the array. So this is going to be our implementation number 2. Very, very similar, except as we go, we are going to store the values in an array and then check if we're running a particular call, check to see if the work has already been done before. And if the work's already been done before, instead of doing more recursive calls, just stop there, pull it out of the array, and we're done. So I'm just going to open that one up for you. And now I've stopped my other one from before. That was not going to finish in any time soon. Exponential time is really bad. So here I'm doing the same thing again, only now I've added unsigned long. Why is unsigned okay to do in this case?
Because you don't have any need for any negative numbers.
Yeah, there are no negative Fibonacci numbers, so I don't need those bits to be used up for that negative bit to be used up for the negative numbers. Right? So I can take even that last bit at the end and say, I'm going to use that bit to represent numbers as well. And how many extra numbers does that give me? So if I have k numbers before, how many numbers do I have now that I'm using that extra bit?
K plus 2?
K plus 2?
I'm not sure.
Maybe give it to Isaac behind you.
What was the question, sorry?
So I have an integer that's of k bits. And now I say you get one extra bit that you can use. How many numbers have I added?
You've doubled.
Yeah, you've doubled
Yeah.
the space available to you because that one extra bit you can use in combination with each of the other ones, possible combinations of the other bits. So by doing unsigned, we've actually doubled the size of the largest integer that we can get up to. So I'm now using unsigned longs, and I'm going to have to adapt my scanf appropriately for this, so we'd have to read the manual. But we know how to do that now. And now I'm just going to create an array of maximum n spaces. And we know that n spaces is appropriate because we know that for the fifth Fibonacci number, we only are going to need 5 slots to store the smaller and recursive calls. We need the answer for f of 5, the answer for f of 4, the f of 3, f of 2, f of 1. So that's what we're doing here. We're creating n slots, each of the size of n, which is just our number that we've entered in here. And then doing the same thing to calculate our call. And now let's take a look at the actual Fibonacci code this time. So it's very, very similar to before. So we have our base case, and the first thing it does is it checks to see if that memory slot is set. If the memory slot is not set, it's just going to set it to 0 over here. But that's probably not necessary because up over here you'll see I've already initialized the entire array to 0. So this line actually isn't going to do anything. We could probably just get rid of it. But this is the important case. So if memory 1 is unset, set memory 1 to be 1. So that's just storing the first Fibonacci number there. And then we have two values, n minus 1 and n minus 2. And really, this is like f of n minus 1 and f of n minus 2. And what it does is it first checks to see if that value in our memory array is set. If the value is set, then we can just use it. That means that we've previously hit that recursive call, and we can just use our saved up value. Otherwise, you're going to actually have to calculate it from scratch. So we make the call, and after we've finished making the call, then we're going to save it in the memory, because we want to make sure that we're actually saving the work when we do it. And it's the same thing for n minus 2. So check if n minus 2 is in the memory, otherwise run the call backwards. Now, is this technically necessary? Do we have to do this check for n minus 2? Isaac, you've still got it, right? Do you want to pass it along one?
You don't have to do n minus 2 because it was needed to calculate n minus 1 and you've already checked.
So we know by virtue... Sorry, I didn't let you finish.
Yeah, you go.
Yeah, we know by virtue of the fact that previously we've just calculated n minus 1 that n minus 2 must already be in memory. So actually, I've wasted some lines of code here, not that they're ever actually going to run, but they didn't need to be in my code in the first place because we could reason that in order to reach those lines, we would have already had to have computed that memory value before. Now you might ask, well, is it a problem that you've added in all these extra lines into your code? And this was actually intentional on my part. And the answer in reality is probably not. And the reason comes down to computer architecture. So when your computer is deciding what code to actually run, if it hits a branch like an if statement, it's going to pay attention to what it's done every other time it's hit the if statement. And if it's familiar with taking either the yes or the no from the if, it's going to make a guess before it actually even starts running that code and start computing those results ahead of time. So because your computer can do multiple things in parallel, it's going to guess ahead and start running that yes branch automatically, which means the no branch isn't really going to run ever, and we're not going to suffer that performance penalty. And this is called speculative execution, and is part of an important part of the design of computers, and something that was only really brought to the fore through security flaws that people found recently. So what about this memory technique? It seems pretty useful, maybe not just for Fibonacci. In fact, we could generalize this technique for a whole bunch of different algorithms, and a class of algorithms we call dynamic programming and dynamic algorithms. And this is just a really fancy way. You'll hear this later in your degrees, hopefully. And it's really just a fancy way of saying, well, we're going to use an array to remember other bits of our algorithm. And we call this process memoization, adding a memory of previous calls to the function. And this is also another useful technique, not just for algorithms development, but for programming development in general. If you find a bit of code that's taking a long time to run, but you anticipate that most of the time it's going to produce the same result, you can remember that result and then do a check whether it's appropriate to restore it or not. So that's a very general technique. So now I'm going to run fib2 and just see if we actually do any better. So I'll run fib1 on something medium size. So it worked on 10. Let's try it on 15. 15 still works. 20 takes a little longer. What about 30? There we go. 30 seems to be a bit where it breaks down. So let's run fib2 and see if we can get to 30. Wow, almost instant. So we can see what a huge improvement this memoization technique made. So let's try fib2 on 70. Still working, pretty good. So in a realistic sense, this is going to be great. Now what about the 100th? Unfortunately, we get an overflow. So think about this as we go along later. So fib2 was already pretty good. However, we can not just get an overflow of an integer, we can also get an overflow of the stack. So you might have heard of a website called Stack Overflow. How many of you have used it before? Everyone? Maya? Never? Okay, thank God. Would have been worried otherwise. So the concept here is that if you're doing recursive calls, you might end up making a lot of calls, and every time you make a recursive call, you add another frame onto the computer stack, onto the operating system stack. And so even if you're not overflowing the individual variable, you might overflow the stack by adding too many of these frames. And there are ways to tell the computer, hey, give me more space for my stack, more space for my stack. But really, recursive algorithms suffer from this problem in that you can't recurse too deeply or you're going to run into this. So you've still got it. Do you want to pass it to Rex? So Rex, what's the alternative to our recursive Fibonacci implementation?
Do you mean recursive for the first one or for this one?
Generally, I don't want to use recursion anymore, but I still want to calculate the Fibonacci
So
number.
if you had a formula, like a function, that if you put in n, it'll automatically calculate it like in maths.
So recursion does something over and over and over and over, right? Yep. And what is the other tool that we can use to do things over and over and over? It's a really simple one. We learned it like the first week.
A loop. A loop?
A loop. We can just use iteration. So anything that is written in a recursive style can always be written in an iterative style, and anything in an iterative style can also always be written in a recursive style. Another good source of exam questions. I haven't seen the exam recently, so I don't actually know if that's on it, just putting it out there. So let's do an iterative version of Fibonacci and try and avoid this problem. So let's now go to Fib3. So here's the same kind of thing, only I'm now doing it with iteration. And it looks pretty similar. In the function, we explicitly say if the values for 0 and 1. And then we just have a loop that keeps track of what it was 2 iterations ago and what it was 1 iteration ago, and then just sums them together. So really not very difficult. You should be able to write this on your own pretty simply. So let's give it a run. Now we'll try 50. Oh, there we go. Runs that pretty darn fast. Now let's run it with 70. Runs that pretty fast. And 100. Is that going to work, Rex?
Can't remember.
So looking at those numbers, it didn't detect the overflow correctly, but we can see that that is
right.
almost certain to be wrong because we were overflowing the integer, not the stack here. So it depends which of these two things is going to grow faster. Are you going to overload the stack too fast, or are you going to overflow your integer too fast? So we still haven't solved that problem. So if we were to look at the runtime of Fib3, we get O of n. Now that makes us much happier, right, Tissan? That is far from exponential. And we only have to store O of 1 values in memory. How many values in memory were we storing for the memoized version, Rex?
I think it was n values.
Yeah, so O of,
O
you
of
just
n.
said it.
O of n.
O of n. So it turns out that the iterative version is actually much better in terms of memory and space because neither are we building on stack frames and nor are we saving all these extra values in memory. So if you're ever approached by an interviewer and they say, write me Fibonacci, you can write the recursive version and then you say, but that version kind of sucks, I'll make it better. And then you show them the memoized version. You say, nah, but that version has O of n memory. I can give you an O of 1 memory version, and then you write the iterative version, and they're like, that's too simple. Okay, fine, that's too simple. So what if we want to run this like 1,000,000 times? What would we do? Rex, do you want to pass it one back behind you? And I don't know your name, despite it being the last day of class, so it's a good time to learn.
Egelina.
You'll have to shout.
Egelina.
Angelina.
Egelina.
So which of these 3 options would we do if we were going to run this program over and over and over and over and over? So I've given you 3 versions, right? The plain recursive version, the recursive version that stores the results, and the iterative version that doesn't store anything. So which would you use if you were going to compute a lot of different values?
Iteration.
Why would you use iteration?
Because it doesn't store the like use the memory to store.
So that's true, it doesn't store things in memory, but in this case I've told you that we're going to be reusing the program a lot and probably reusing a lot of the values. So which would be the right choice then?
Recursion.
The first recursion or the second one?
The first one.
The first one didn't actually store anything. It just added more stack frames and more stack frames. So the right answer here is actually number 2, where we've created this array that has stored all the different results of the recursion before. So it's not quite so simple as I told you a second ago. It's not just always use the iterative version. If you were going to use version 2, and instead of just storing the array in memory, but you wrote it out to a file after and then read it in whenever you started the program, you could skip most of the work most of the time, just at the cost of O of n memory. But now we've got another challenge. What if I want to run it with big numbers? Then we have the problem that we saw before, where fib1 and fib2 get both stack and integer overflows, and fib3 was immune at least largely from the stack overflows, because we got to the integer overflows before we got to the stack overflows. But we're not done. What if I want to run it with really big numbers? So this is another question that you could get in your programming interview. Nathan, Angelina, do you want to pass it back behind you, one row? We're going all the way to the back so I get a good angle. What should I do if I want to run this with really big numbers?
Is there a data type that's even larger than a long?
So there isn't a built-in data type. What could we do?
Is there a library that has one?
There is a library that has one, so that's the cheap answer. And what else could we do if we don't have a library on hand?
I guess we could put the digits in like an array and then compute the addition.
Yeah, so an array might not be the absolute best data structure to do this, but essentially that's how the libraries work, is they use a struct or some other form of data storage to actually store all the digits, and then they redefine the mathematical operations such that you can run on that. But is that going to be super efficient?
Probably not, no.
Probably not. The reason a lot of our operations are efficient right now is because our hardware is optimized to deal with what we call the word length of the integers. There's some default size that our system architecture is just wired up to run efficiently, and as soon as we do what Nathan suggests, then we're going to start slowing things down pretty significantly. So I have one solution to us. We could use that library to store the big numbers, but our general operations are not going to be fast, so maybe we can just come up with an O of 1 formula. And this is called Benet's formula. And it is a closed form solution to the nth Fibonacci number, where phi here is the golden ratio. So rather than writing this whole fancy algorithm, we can just do this computation. So where f of n equals, I will open this up. Oh. And this is the Benet's formula version of my Fibonacci program. And I think there might have been a typo on the previous slide that I'll look out after if I use the wrong symbol in 2 places. But essentially, I just compute it directly, and that's it. That's the whole thing. And let's calculate the 30th Fibonacci number, and you can see that was, it's hard to tell the difference when you're just running it once, but that was as good as instant as we're going to get. Now let's run it with the 50th. Will it work for the 100th Fibonacci number? Nathan? It's a not certain yes. So it looks like it worked, but we don't actually know. Now the problem here is that we can still run into our integer overflow for the result. I haven't used a library here to actually give myself more space, and so we're still going to run into our overflow problems. And this tells you something to watch out for. Even if it produces an answer, doesn't mean it's doing it correctly because of the way that integers wrap around. And so just like all of you have experienced with your projects, where the program runs and seems to work, but actually doesn't do what you think it's doing because you have a bug somewhere, maybe you've overwritten some memory. When you run it on 2 different computers, it behaves differently. So that's always a bit of a problem for us. Now let's pass it on to Hamish or Maya? Flip a coin. Okay, Maya's got it. Sorry, you lost out this time. What is the runtime of the Béné's formula version?
1 of 1.
Why is it O of 1?
Because you're just like doing the multiplication and the division.
So we're doing multiplication, but if you think about how the circuitry of the computer is designed, does that seem accurate that when I calculate phi to the 100, there's a circuit that calculates things to the power of 100? No. So what do you think is actually happening under the hood, if you had to guess?
I don't know.
Don't know? Well, what do you think the computer does if you tell it to do exponentiation? How would you do exponentiation normally? Like if I tell you calculate 2 to the power of 10, how would you calculate that?
Multiply it repeatedly.
Yeah, you do some kind of multiplication process, and there are ways to speed up the process, but ultimately, at the end of the day, you're going to have to do some repeated work. And this kind of exposes the lie that we've been talking about in our model of computation at least, which is arithmetic operations are not really O of 1, and this is going to become more important when dealing with larger and larger numbers, particularly those that we use in my field, cryptography. So when you start getting to really large numbers, you stop being able to trust this O of 1 simplification, which is good for certain types of analysis, but for other types of analysis, when you think about the world in which your algorithm is going to run, this no longer becomes appropriate. So this is a lesson, again from the class, is that the algorithmic complexity of a given program is going to depend on the size of the inputs and the outputs and the data types, and gives us a little more exposure to the fact that algorithmic complexity has much more beneath the surface than we really thought. So what's the most efficient runtime that we can get? Maya?
Well, I think for multiplication, it's n log n.
I think there's an n log n algorithm. There's
Yeah.
also Karatsuba's algorithm, which is a super fancy one that I think uses Fourier transforms that is really cool. But the way you do exponentiation is normally something called square and multiply. But we can talk more about that after. Definitely not part of the curriculum. So what is the most efficient runtime that you think we can get for Fibonacci?
If you pretend that multiplication is O of 1, or if you don't.
So that one, like, let's stop pretending that multiplication is O of 1. Can we actually get O of 1 runtime? And do you have an idea of how we might do that? I've already given you a closed form solution. Can we do better?
Maybe if you like calculated them beforehand and stored them somewhere, and then. If
Maya, that was a stroke of genius. In 4 years of teaching this class, you are the first person who's gotten it right off the bat. So this is Fib 5. Very pleased with you. If I had a chocolate, you would get it. So this is Fib 5. I have a table of all the Fibonacci numbers that fit within a long, and I've computed them ahead of time. And now when I run the program, if n is larger than 90, well, we'd get an overflow, so nothing. Otherwise, just fetch it out from memory. And this is an O of 1 solution. And you might laugh, you might say that's totally ridiculous. But in this case, it's actually perfectly reasonable because the cost of storing these Fibonacci numbers is probably not that different from storing the code itself to do the recursive version. So if you want to be a real smartass when in a programming interview and someone says, write me the best version of a Fibonacci algorithm that you can, write this out, they'll say, well, no, that's kind of cheating. That's not what I asked for. That doesn't actually compute the Fibonacci algorithm. And you say, well, actually, Dr. Connie told me that this is the implementation that makes the most sense when we only have fixed size integers available, because everything else you're just going to run into integer overflow anyway, and the code that I've written will take up more memory than storing the table itself. So this is Fib 5, and of course we're going to run it. Yeah, this is almost the most optimized you could go. You could go a little better if you maybe wrote it in assembly code, but in a minute, Gabriel.
But is it optimized for your brain?
Ooh, okay. So there we go, instant result. And what is the lesson from all of this? The real solution is going to depend on the real context of the problem. So the problem with these programming interviews is that it's a totally artificial context. And in order to actually determine the right solution, when someone asks you to write, say, code that does Fibonacci, you need to figure out, okay, is this code going to run multiple times? Do I need it to represent really big numbers? What kinds of computers is it going to run on? Is this going to be distributed? How are the results going to be used? And this is going to determine which of these solutions is actually the right one to use. So the main message from our whole class is that designing algorithms requires some careful thought about a number of different factors. So what is the problem, and what are your constraints around the problem? What are your inputs going to be? What are your outputs going to be? Then we're going to ask, what are the theoretical characteristics of your solution? So what is the big O runtime? But with almost every one of the algorithms that we've shown in class, the theoretical runtime wasn't enough. We would then go and test it empirically. And this is something that's also important in computer science research and in algorithms research. A lot of early research focused much more on theoretical characteristics, doing proofs. But then people realized that to actually get the full benefit of the constructions, you needed to also figure out how they would run on real computers. Now, often there may be a gap between these two things, and your practical performance will be a lot worse than theory. This is, for example, true in the case of heap sort, which didn't perform as well as quicksort on many real inputs. And there you can dig in and understand why this is the case, and also develop better theoretical pictures that do allow you to characterize your algorithms more precisely. But again, our message before, understanding which of these theoretical or which of these practical solutions is going to apply depends on your context and depends on your model of computation. So this is one main message that we could take away. What's the real message of the class? And with that, that's the end of Foundations of Algorithms. You're on the phone with your girlfriend, she's upset. She's going off about functions, trees, and sets, 'cause her code just doesn't compile when she tries to. I'm still on Zoom, it's a typical Wednesday night, making lectures and find something that you'll like. A big brain, maybe giant cards, and some costumes too. She forgot asserts, her code won't convert Fahrenheit to Celsius, it's lacking any features. She's dreaming about the day when she wakes up to find that bug she's looking for could be fixed on one line. If you could see that FOA is not hard to understand, you'll find that all along you were learning C, and now it's easy. It's so easy. You're eating treats, it's a Sissa scene. You're in Melbourne Connect, where we start at 3. Laughing with your laptop, thinking to yourself, hey, isn't this easy? But now it's a while and your face is in a frown. You corrupted a file, your code is going down. You say you're fine, I know you're better than that. Hey, what you doing with a seg fault like that? Late night cheap eats Swift on the speakers. Find teaching fellows more helpful than the teachers. Dreaming about the day when you wake up and find your friends from FOA will last for all time. You could see that FOA is not hard to understand. You'll find that all along we're learning C, and now it's hope I've now deleted every backdoor. Every last malloc is now matched with free memory in C. Memory in C. Oh, I remember when John Jones in the house, yeah, he makes us feel alright. Cringy jokes that get a laugh with Dr. Connie's silly ties. Though semester isn't long, we can still go on and dream about the place where you and now it's easy. Hope I've now deleted every last block. Each and every malloc is matched with 3. Memory in C. You all know C. You all know C. Have you ever thought just maybe